to the next talk given by Dimitris Giannakis on quantum computer for classical dynamical systems. And Dimitris is an associate professor of mathematics at Courant Institute, NYU, and he's also affiliated with Courant Center for Atmosphere, for atmosphere, ocean sciences. He received bachelor and master degrees in natural sciences from University of Cambridge in 2001 and PhD in physics from U Chicago in 2009. His current research is focused at the interface between operator theoretic techniques for dynamical system and machine learning. His recent work includes the development of techniques for coherent pattern extraction, statistical forecasting, and data assimilation based on data-driven approximation of Hopman operators of dynamical system. He has worked on application of these tools to atmospheric and ocean sciences, fluid dynamics, and molecular dynamics. Welcome, Dimitris.
Thank you very much. I'd like to start by thanking the organizers for putting together this great event and for giving me an opportunity to present our work. So I'll be talking today about ways of embedding classical dynamical systems into quantum mechanical systems which are amenable to quantum computation. I'd like to thank my collaborators on this work, Abbas Urmast, Jörg Schumacher, and Joanna Slawinska. Also acknowledge support from ONR and NSF. So as a motivation for this work, I wanted to show an excerpt from a classical paper of Feynman from the 1980s, where he posed the question on whether physical systems can be simulated by universal simulators or universal computers in his word. So his motivation to study that question was that concerned basically the simulation of quantum mechanical systems, which were, according to current theory, nature is fundamentally quantum mechanical. And such systems are basically exponentially expensive to simulate by means of classical computers in the number of particles. So what he was positing is whether we should be using quantum systems to simulate quantum systems as a way of addressing that limitation. So what I would like to talk about here today is kind of like the converse of that question. If in some sense, if simulating quantum mechanical systems by classical systems is an exponentially hard problem, perhaps simulating classical systems by quantum systems is an exponentially easy problem, and that maybe can help us design algorithms with very strong sort of scalability properties. So this is a problem that has been studied to some extent, perhaps not as much as the other problems. So here I'm just listing a few representative works in the literature, starting from the early 2000s, where there has been work on discrete time dynamical systems, other examples related to differential equations with certain types of nonlinearities. We have done some work on ways of posing data simulations as filtering in the language of quantum theory and quantum probability, with some combinations with machine learning. More recently, there has been work on the so-called Koopman von Neumann formalism, which is a way of embedding a classical dynamical system into a quantum system by using a sort of extended Hamiltonian. And very recently, there has been also interest in potentially using quantum computational techniques to simulate complex fluid flows, like turbulent fluid flows. So what I would like to talk about today is to describe a framework for embedding classical dynamical systems into finite dimensional quantum systems, which is amenable to quantum computation. So it's basically scales in favorable ways as the number of qubits or quantum bits of the system increases. So I will loosely refer to this approach as a quantum compiler, in the sense that it takes as an input a deterministic dynamical system, which is prescribed through a set of differential equations, and its output is a stochastic simulator of the evolution of observables of the system, which is realized through quantum measurement, as I will describe. So I want to start by giving a very brief overview of the basic axioms of quantum theory as posed by Dirac and von Neumann. And so the initial building block in the construction of a quantum system is the specification of a Hilbert space over the complex numbers, and that can vary very strongly depending on the system. So this could be a finite dimensional Hilbert space. So when you're dealing, for example, with collections of interacting spins, or it could be a function space when dealing with systems like a particle in a box. That depends very strongly on the system. But once an appropriate Hilbert space has been specified, the state of a quantum system corresponds to a so-called density operator on that Hilbert space, which is basically a positive operator of trace class and unit trace. So you can think of a density operator as being somewhat analogous to a operator theoretic or non-commutative version of a probability measure, if you wish, and we are characterizing the state of a quantum system by such an object. So basically, something like a matrix. Right? The state of the system is going to be described by a matrix, in effect. And observables of the system are going to be linear operators, self-adjoint linear operators on that Hilbert space. Unlike, for example, classical physics, where observables are typically functions on a state space. So the next aspect that I want to mention is how does dynamical evolution proceed in quantum theory. Basically, it proceeds by means of unitary operators on that Hilbert space, which are typically generated by a Hamiltonian, but they can be pretty general again. And these operators act on the state space, on the set of density operators in this manner. So basically by conjugation, and they induce a unitary evolution. Now, quantum theory also describes what are the outcomes of physical experiments. So we mentioned that observables in quantum mechanics are self-adjoint operators, and that's somewhat abstract, but concretely, what quantum theory posits is that the outcome of performing physical experiments to measure quantum mechanical observables correspond to the spectra of the corresponding operators. So since we have self-adjoint operators on Hilbert space, there is a spectral resolution. You can express your operator by means of an operator valued integral over a spectral measure. So this is some type of, you can think of it as an infinite dimensional generalization of how you would write a self-adjoint matrix as a linear combination of projections onto the eigenspaces weighted by the corresponding eigenvalues. And the claim here is that the spectrum of this operator gives us the possible outcomes of physical experiments measuring the observable A. Now, moreover, when the system is in a particular quantum state, we have a formula that gives us the probability, or first I should say the expectation of value of an observable, which is given by the trace of the density operator times the observable in question. So you could think of this again as some type of, as being somewhat analogous to taking the integral of some function with respect to some probability density, where the trace here would be the analog of the notion of integration, let's say in classical probability theory, and rho would be analogous to a probability density. So that's the expected value of experiments. And moreover, we also have a procedure to determine the probability of measurements lying in subsets of the real line, basically by computing the expectation of the corresponding spectral projectors. So you could think, in some sense, the spectral projectors here as being analogous to characteristic functions indexing events. And finally, there is a version of effectively Bayes theorem for quantum states, which tells us how to update a state when the system has actually been measured, when an observable of the system has actually been measured, and there has been a result lying in the spectrum of the observable. I'm not going to use this in this talk today, but it is important, for example, in the context of data assimilation, when you want to observe the system sequentially in time. Okay, so we have these the basic building blocks of a quantum system. What I'd like to do next is kind of like sketch the procedure, a procedure at least, of mapping a classical or dynamical system into a finite dimensional quantum system, and doing that in a way that is sort of compatible with a classical evolution. So at a classical level, we describe a dynamical system by a state space, so that that could be a manifold or some other topological space, and there is an evolution map that takes states to states for under evolution for time t. So the first step in this procedure is to take this classical evolution and embed it into what I'm referring to here as classical statistical evolution. So P of x here represents the set of Borel probability measures on our space, and we can take basically points in X and embed them into probability measures by basically mapping them to the corresponding Dirac delta function. So this is what this delta here signifies. And on the space of probability measures, the dynamics acts by means of the push forward map on measures. So we heard an example of that earlier today in Tom Howe's talk in a different context. But the point is that this diagram here commutes. So we can consistently embed a classical dynamical system on state space into an evolution in a space of probability measures. Now the next step, which I'm going to just sketch now and then describe in more detail, we want to embed this classical statistical space, so the space of classical probability measures, into a space of quantum states, which will be well, as I mentioned before, the space of trace class operators of unit trace on an appropriately chosen Hilbert space, which will be here later on. This will be some reproducing kernel Hilbert space with additional structure. So we're going to prescribe a mapping that takes classical probability measures into quantum states, so embeds them into quantum states in a manner that there is another commuting diagram for an appropriately chosen evolution map at the level of quantum states. So this is going to be an infinite dimensional Hilbert space. So this is an infinite dimensional quantum mechanical system. Now what we want to do next is actually project this to a finite dimensional quantum system. So there will be a next step to arrive at what I refer here as a quantum computational level, where now we have a space, a Hilbert space B sub n, which will be the Hilbert space associated with n qubits. And so this is a finite dimensional Hilbert space you can think of this space Bn as being isomorphic basically to the tensor product of n factors of c to the power 2, where that's the Hilbert space associated with one qubit, and we have n being our qubit, and the dimension of this space is basically 2 to the power n. So this is what effectively gives us quantum scalability or quantum parallelism. And we want to construct this projection in a manner that, as I will explain in more detail below, on the one hand, there is a diagram here that, again, commutes, but on the other hand, the quantum mechanical evolution at this level can be done very efficiently, namely through quantum channels that don't have a lot of logical or quantum gates. And by increasing n, the number of qubits, we get an exponential increase in the dimension of the Hilbert space in which we define our quantum system. Okay, so this is the general procedure, and I will go on to describe it next in more detail. Before I do that, I want to mention a bit of a disclaimer, and namely this is we're basically just getting started with this. This is more of like a first step in this direction, at least for us. So maybe if I can make a comparison, we are sort of at the level of punch cards, as opposed to, let's say, modern compilers. So I won't be showing results here for any by any means any complicated dynamical system, but I think at the very least we have a framework that, in theory at least, should be able to, with appropriate modifications, address complex systems. Okay, so with that sort of disclaimer out of the way, let me start by introducing, as a concrete example, the class of dynamical systems I will be talking about in this work, and namely this will be ergodic rotations on tori. So the state space of the system is going to be a smooth manifold, a d-dimensional torus, on which we have an ergodic rotation. So what that means is that there are d parameters here, these alphas, which are frequency parameters that are rationally independent, such that when under dynamical evolution under this map, the orbits basically do not close, they do not form circles embedded in the torus, but rather they densely sample the torus as time increases. So this might appear somewhat contrived, and in some sense, it's by no means like a general ergodic dynamical system, but it is actually a canonical representative of a much wider class of systems which have a discrete or like a pure point frequency spectrum, which is generated by finitely many frequencies. So these alphas. So this is actually, I think, a rather useful model. And towards the end of the talk, I will probably say a few words about how we could approximate a system that doesn't fit in this category, namely a chaotic system that has potentially continuous spectrum with a system that has a discrete or a point spectrum, like a ergodic rotation on a torus. So we're going to take this as our model example. And since we're working our way towards building a quantum mechanical system, the first thing I want to mention is how we choose our Hilbert space. So for us, the Hilbert space is going to be a space of functions on the torus, complex valued functions on the torus, which we're going to build as a reproducing kernel Hilbert space. So one advantage of being on the torus is that the torus, besides being a nice, smooth, compact manifold, it's also an abelian group. So we can use tools from Fourier analysis and representation theory on abelian groups to build our function spaces. And we can take in particular the Fourier functions, which are the characters, unitary characters of the group, and create kernels through this type of so Mercer type expansion. The specific kernel construction we're going to employ here is going to be based on these coefficients, these spectral coefficients lambda sub j, which are defined in this way for a choice of parameter p and tau. And what I want to point out here is that what is important here is that we choose this power here, this parameter p, such that the function, j to the power p, is a strictly concave function. This is actually important for our construction. So in work with my former postdoc, Shutho Das, what we have shown is that the reproducing kernel Hilbert space induced by this choice of kernel is, on the one hand, is a dense subspace of the space of continuous functions. So it's a sufficiently rich space as a space of observables, but moreover, it has the additional special property of being an algebra under a Banach algebra under pointwise multiplication of functions. So in particular, while a general RKHS need not be closed under products of functions, for this choice of kernel, the H actually is closed, and this will become important for us later on. So we have this additional algebraic structure in the space. We're going to call this space an reproducing kernel Hilbert algebra. As a side note, I could mention that this choice of kernel here is related to some class of fractional diffusions on the torus. And also for notation, we're going to use the sort of standard orthonormal basis that one gets for the RKHS that one gets from the Mercer expansion, which I'm going to call psi sub j. Okay, so this is our Hilbert space, and now, I guess I wanted to just make a brief note here, comparing various types of spaces that one could employ on the torus, like L2 spaces or spaces of continuous functions, or smooth functions, or general RKHSs. What we are striving for here with this RKHA construction is to have as many sort of properties as possible that would facilitate constructing a quantum system. And for us, this star algebra, this Banach algebra structure is going to be important, as well as of course the Hilbert space structure, since we want this to be sort of the building block for a quantum system. Okay, so one final thing before I actually jump into the construction, we want to specify a unitary evolution, as I mentioned earlier, as part of the definition of the quantum system. And the natural choice in this case is to use the Koopman operators associated with the classical dynamical system. These are the composition operators by the dynamical flow. Tyrus mentioned this also in his talk earlier today. So it happens that for the class of ergodic, torus rotations we're looking at, the RKHS is invariant under the composition by the dynamical flow. And in fact, the group of operators one gets in this way is a unitary evolution group. So we can characterize it by means of its infinitesimal generator, which is a skew adjoint operator, which we can think of as being somewhat analogous to a Hamiltonian in quantum theory, even though here we're not assuming that the dynamics is actually Hamiltonian in the sense of having a position, momentum variables, and so on. Nonetheless, we have this generator, which has an point, it's diagonalizable in the basis, in the canonical orthonormal basis of the RKHA. So this is an important property that will make a lot of simplification, lead to a lot of simplifications later on. In particular, when we act with a generator on one of these RKHS basis functions, we get an eigenvalue, which is a linear integer, linear combination of the generating frequencies of the rotation. And the spectrum of the generator is closed under addition, and likewise products of eigenfunctions which stay in the RKHS, since it's a Banach algebra, they are proportional again to eigenfunctions with some coefficients here as proportionality constants. Okay, so so this is we have now the basic ingredients. So we can go through the steps that I mentioned before in a little bit more detail. So the first step is takes us from classical dynamics on state space to this classical statistical dynamics. I'm just repeating here what I said before, that we use the Dirac measures to basically represent points in the underlying state space, and the push forward map on measures to represent the dynamics, and this is a basically commuting diagram. Now the next step is we want to go from the classical statistical space to this quantum state space, which will be, we're going to use our RKHS as the defined before as the Hilbert space, and we're going to consider the set of trace class operators of unit trace, positive operators of unit trace, as our quantum states. And in order to consistently embed the classical statistical dynamics in this space, we're going to use basically feature maps associated with reproducing kernel Hilbert spaces. So the canonical classical way of assigning a feature map associated with an RKHS is to basically map points in the set X into kernel sections by this through this formula, and we can sort of lift this to the quantum level by instead of considering maps that take values in H, we want to consider maps that take values in Q of H, the sets of quantum states on H, which basically we're going to do by assigning rank 1 projections along the corresponding feature vectors. So we take our feature vectors and we create the corresponding rank 1 projections for the choice of kernel that I prescribed before. This is an injective map. So we're putting first of all, we can put points in X into Q of H, but we can also do be slightly more general. We can define an embedding of classical probability measures into quantum states using a formula that basically it's reminiscent of the RKHS embedding of classical probability measures. Basically, you integrate against this feature. There is this feature, the values of the feature map, and with the difference here that we have an operator valued integral. So this basically gives us the procedure of going from classical statistics to quantum statistics, and then in this space, the natural choice for evolution that closes this diagram is to consider unitary evolution under the Koopman conjugation by the Koopman operators according to this formula. So now we have basically embedded a classical dynamical system into the state space of a quantum system. I want to say now what we do for observables. And this is where this algebraic, this Banach algebra structure of H comes, it becomes very handy. Basically, because we have an algebra structure, there is a regular representation of the algebra. So basically a map that takes elements of H to bounded operators on H. So H is of course, a Hilbert space. And basically what this map does, it takes functions and maps them onto the corresponding multiplication operators, which are guaranteed to lie in H because of the algebra property. And it does so in a way that makes this diagram here commute, where the script U is a unitary evolution of the bounded operators in H, given again by conjugation with the Koopman operator. Now, for our purposes, since we are going to be interested in realizing this framework using quantum mechanical measurements, we actually want to consider maps that take values into the self-adjoint operators in H. So I'm going to define here a symmetrized or self-adjoint version of pi, where we basically take the self-adjoint part. This is injective if f is a real valued function. So which for purposes of sort of simulating physical systems, that's this is sufficient. Okay, maybe I can make a quick pause, and in case there are any questions here, I could answer before I describe how we build a quantum computational representation of the system.
Right. If anyone wants to ask questions, please go ahead.
Otherwise, I can just continue. Maybe I will just continue. So
okay.
So we have our so now the next part of the procedure is to describe how do we go from this infinite dimensional quantum mechanical system to a finite dimensional one in a manner which is efficient from the point of view of quantum computation. Okay, so let me just I'll just briefly I'll just skip that for now. Sorry, yes, I forgot to mention this point before I go into the quantum computation, which is actually important. So yes, we've described this procedure of mapping down to the quantum mechanical level, but of course we want this to be consistent with the system that we started with, right? Otherwise it would not be particularly useful. And I just want to point out that there is a consistency relationship between dynamical evolution of classical observables in H with quantum mechanical expectation values evaluated on this quantum feature map and using the regular representation or this self-adjoint map T that that I described, and the fact that H is a reproducing kernel Hilbert space as opposed to, let's say, an L2 space is actually important to get this type of consistency. So the reproducing property was used to derive these relations. Okay, so we have now this fully consistent representation. Now we have to go down to finite dimensions in order to perform quantum computation. Okay, so now, as I mentioned in the beginning of the talk, the space that we want to arrive at the end of the day is this 2 to the power n dimensional Hilbert space, which is associated with n qubits, where we can think of a qubit being a quantum system associated with the Hilbert space, 2-dimensional Hilbert space C2. So on this space, we have a sort of distinguished operator, the Pauli Z operators. You can think of this as sort of identifying between spin up and spin down states, which has a orthonormal eigenbasis, which I'm going to denote here by these 0 and 1 vectors, and I'm using the Dirac bracket notation for this part of the description. So this will be our canonical basis vector for the qubits, and when we go to this tensor product space, correspondingly, we have a tensor product basis that we can characterize by basically supplying a binary string of length n, and that gives us one basis vector here. So we're going to use this notation later on. So I basically, let me see here the time. Sorry. Yeah, so maybe I'll skip the full details here, but what I do want to point out is how basically we can, there are 2 steps in this procedure. On the one hand, we want to identify, since our original system was defined on this Hilbert space H, we want to identify, first of all, 2 to the power n dimensional subspaces of that space. And then we're going to take these 2 to the power n dimensional subspaces and map them down to this tensor product space associated with the qubits, with the n qubits. in a way that the Hamiltonian, the generator of the system, will become basically factorized in a tensor product. And this is what will enable quantum parallelism. And sort of as a sketch of how we do it, we start first by identifying this sort of index set where we go, we pick an integer n, that's the number of qubits, and we have it such that it's divisible by the dimension of the torus we're working with. And we're going to take these indices here where we basically skip the 0 index. And then form this, basically take the Cartesian product of this index set. So this is like a 2 to the n element set, and identifies for us a 2 to the n dimensional subspace of H, which I'm going to call Hn. So without sort of going through maybe this cumbersome notation, we can construct analogs or variants of these the feature maps that we had described before, and basically the maps also for the observables, such that as n increases, so that's the number of qubits, we have the same sort of consistency as we had before. So we can basically now focus on our system in this 2 to the n dimensional subspace of H, and consider, think about the asymptotic limit of infinite qubits as where we achieve convergence to the original system. But now we need to describe how we go from this H sub n space to the tensor product space associated with the qubits. Sorry, I'm skipping here a few things just because I want to make sure I get to the end of the talk and on time. Now, the way this is done is we are going to basically what we need to do, we need to assign to every basis element of our subspace Hn a binary string. That's how we're going to map it into this tensor product basis. So we can do that basically by there are many ways of doing it, but one way that is going to be useful later on, we can basically simply order the elements of our index set from 0 to the 2 to the power n over d minus 1. So we're skipping the 0 index in this set. And for this ordering, which is a non-negative integer in this range, we can compute the dyadic representation of that integer. And we do that d times, so we're in this d-dimensional torus, and we sort of concatenate these, binary strings of length n over d that gives us a binary string of length n, and we're going to say that we're going to map the basis element of the RKHS that is associated with index j to a binary string, to the corresponding basis element of the qubit space that corresponds to this basically binary string. Okay. So that it defines a unitary map, and we can choose under this map, we can sort of push forward our dynamical evolution in the original space. And basically, we have a commuting diagram again. So now we're down to this space here by doing this projection. We want to look at how the generator of our dynamics is represented in this basis. So that's kind of the key thing to enable us to have efficient quantum computation. And here we found some work in the literature that was very handy. This work of Welch et al. It's a paper in the New Journal of Physics where they basically did pretty much exactly what we needed here. Is basically what we want. We want to factorize the generator of the system. When we sort of push it forward into this tensor product space, we want to factorize it into a sum of operators which are basically in pure tensor product form. And there is a procedure that they have established, which basically involves taking an operator which is diagonal on this qubit basis and decomposing it in a sum of this form They call these operators here, Z sub n, they call them Walsh operators, which are basically tensor products of Pauli Z operators with some indices, power exponents here, which are given by different binary strings. And there is a constructive procedure of taking your original operator. You have to do a type of Walsh Fourier transform of the essentially the eigenvalues of your operator, and that gives you the coefficients in this decomposition. Okay. So what we do here, we apply it in the case of the generator, of the Koopman generator from our original system. We basically apply the procedure of Welch et al. To produce this tensor product decomposition. And what is the interesting thing that happens is that for the particular class of like operators, the generators of ergodic dynamical systems with pure point spectra, which I here refer to as quasi-periodic systems, this spectral function here, so how omega depends on J, conspires, so to speak, in a way such that in this Walsh operator representation, the resulting Hamiltonian at the level of the quantum computer factorizes in a way that all the operators that appear, there is only one Pauli Z operator in each factor. So, and that's hugely important from the point of view of computational efficiency, because then we can, when we exponentiate this Hamiltonian to generate dynamical evolution, basically it can be done in a fully parallel way through this tensor product factorization. So this can be implemented. This can be implemented in a quantum circuit, and because of this factorization that that I described, one can implement this evolution in a quantum circuit where there is no communication between the channels. So there is basically the number of gates that you need to implement the circuit grows linearly with the number of qubits. And of course, the dimension of the Hilbert space that you span grows exponentially with the number of qubits. So it appears that pure point spectra, dynamical systems with pure point spectra, are almost ideally suited for quantum computation in the sense that you can, without any communication with between the qubits, you can simulate them sort of with exponential scalability in this case. Now, of course, when we go to systems, and this is something we're working on at the moment, which are chaotic, then the corresponding Koopman operator will not longer be of this quasi-periodic or pure point spectrum type. But we have techniques of approximating these systems by systems which are of pure point spectrum. And so in general, we would expect to have more interchannel communication in such cases when you have chaotic dynamics. And it will be, I think, an interesting question to think about ways of sort of optimizing this procedure. Okay, so I'm running out of time. So, but what I want to sort of maybe quickly go over and wrap up is to describe how given that we've performed this construction, how do we actually query this system? How do we actually obtain predictions, right? And this basically goes under the umbrella of quantum measurement theory, having to do with basically spectral resolutions of operators, as I described in the beginning of the talk. So very quickly, when we are in this n qubit computer, there is an associated what we think of as being the quantum register. So there is a projection valued measure that is defined on basically on subsets of n bit binary strings. And basically, if you think about the process of measuring the quantum register in a given state that the quantum computer might have, basically what you're doing, you're returning a random binary string of length n with a probability that is given by the trace of the state of quantum state of the computer evaluated times the spectral projector associated with this spectral measure. And basically, using this formula, what you can do is you can take remember we have a map that takes the classical observables into self-adjoint operators, and these have a spectral resolution. Now we're in finite dimensions, 2 to the power n dimensions. So we have a resolution in terms of these real eigenvalues and an orthonormal eigenbasis. And so what we can do, we can rotate the state of our quantum computer that we have reached at time t using basically this quantum feature map and so on, as I described, such that our observable here is diagonalized on that state. And when we do that, we can measure the state of the quantum register so we can measure the spectral measure at E on that state, and that will give us a random number. We can do this independent k independent times, and that gives us some type of Monte Carlo type estimator of the expectation value of this quantum mechanical observable, which basically converges as we let the number of trials go to basically increase. Also, the variance of this estimator decreases as we increase n, because of the previous results I had shown. Okay, so I'll end here very briefly. In a moment, just I want to show some synthetic results for a very simple dynamical system, which is
we're a little bit out of time, Dimitris.
Yes. Yeah, so I'm just going to end here just to show that there is consistency. As you increase the number of qubits, you can get probabilistic predictions of observables, in this case of a rotation on the circle, in a manner that is basically consistent as the number of qubits increases. So I'll stop here. Sorry for running a little bit over. I'll leave here some references, and thank you very much for your attention.
Well, thank you very much for excellent talk. And are there any questions? Please, floor is open.
We have one question in the chat asking, does the factorization have to be done in a classical computer?
That's, if I understand correctly, if my interpretation of the question is correct, it's asking whether we need a classical computer first in order to construct this quantum mechanical system. And I think that's a very good and very valid and interesting point. I wouldn't go as far as saying that we need a classical computer in order to construct this necessarily. But what I think is a fair point is that since we're using this operator theoretic language and techniques, like basically feature maps from reproducing kernel Hilbert spaces and the like, what we do need, at least in the current formulation of this method, we do need data generated from the system. We do need to have samples, at least of small trajectories. I didn't talk about that here, but if we were to assemble, I think I had made a point in the conclusion that if we were to assemble, we would try to assemble this reproducing kernel Hilbert algebra from data. We would use some type of feature-based method, and for that we would need to have at least segments of an ensemble of trajectories of the system. And the question then becomes, how do you get these trajectories? And maybe for that, yeah, you would need a classical computer. Maybe a saving grace here is that you don't need the trajectories to be very long, right? You don't need one very long trajectory. You could apply the scheme for using an ensemble of short trajectories. You could potentially construct in parallel, so to speak. But I think, as with a lot of other, this is not unique to this method. As with a lot of other techniques, yeah, you do need to provide, at least the way we have it set up right now, you do need to provide data if you were to do this in a data-driven way.
So I have a question. When you're constructing your Mercer type kernel, right? Basically, as I understand, is that you are constructing an RKHS to be spanned by eigenfunction of fractional Laplacian.
Yes.
So you mentioned that, and I wonder, how important is that to represent that in order to, is that the key things to get the algebra?
Yeah, so what the algebra property we need in order basically for this type of construction to work. Basically what we want to ensure that we have an RKHS that has a non-trivial multiplier space. Basically the set of elements of the RKHS that correspond to bounded operators under multiplication. At least in the way we've set things up thus far, we need this type of to have that structure available. So so for a general RKHS, this is not true. Even though there is a lot of work on multiplier spaces of RKHS. So for example, if you took the heat kernel, not like a fractional diffusion, like a regular diffusion on the circle, and you look at an RKHS that is associated with a heat kernel, it's not closed under products of functions, intuitively because it has too much regularity, so to speak. But by using this slightly sort of weaker decay of the eigenvalue, so instead of, for the regular heat kernel, it would be j to the power 2 here.
That's right.
Here we're taking p to be strictly between 0 and 1. In fact, we're not even allowing the case 1. And it seems that this is enough to ensure that this property holds here. Basically. But you don't decay so rapidly like this.
Yes.
So if any other type of construction that I think satisfies similar or has similar properties, I think could be employed here. I don't think this is particularly special, other than basically ensuring this condition.
The next question, let's see, do quantum algorithms provide any significant advantage over traditional methods for control of non-quantum dynamical systems? I mean, I'm wondering also about sort of the this is from the chat, but I'm wondering also about sort of, is the point here that you get convergence that's big O of like 1/2 to the number of qubits or something like that?
Well, I think the hope is that well, in an ideal world, the convergence would be e to the minus n, right? Like where n is the number of qubits, because basically the dimension of the subspaces of H, where the sort of the quantum computer lives, grows exponentially with n, right? So basically, if you have capability of increasing, your qubits, the dimension that you are able to span, the dimension of the subspace increases exponentially because it's basically a tensor product of. So the hope is that if at some point in the future there are these computing platforms available, of course, I'm not by any means claiming that this is something that you could do today, but if to the extent that such machines become available, they would provide very strong scalability with n. Like the control parameter here would not be the dimension of H itself, would be the number of qubits, and the dimension of H is like 2 to the power n. I'm not sure if that's answering your question, Tyrus.
That's definitely answering my question. I'm not sure if it's
the control part. I think that's also very interesting. I don't have an answer for that, but it sounds like a natural thing to think about. Whether, if I understood correctly, the question was whether this quantum description could be useful also for classical control. My hunch is that there might be some interesting directions to take in that general area, because yeah, you could imagine the control actuators. You could describe them as sort of operators in the quantum level, analogous to how you have a vector field of a dynamical system generates a dynamical system. It's also an operator. It's a differentiation operator in a space of functions. And similarly, the same thing can be done for the actuators that are used in a control system. And then you could ask, if I have a control schedule, I'm taking linear combinations of these operators, and I can generate different evolutions by exponentiating. And I suppose that there should be, and I'm definitely not an expert by any stretch of imagination in control theory, but there should be ways, I believe, of interesting ways of thinking about control problems in this language.
Let's see, is it possible to connect the dynamical system directly to a Schrödinger equation?
Well, I think there are some of the techniques that I mentioned in the beginning. They do this perhaps more explicitly than is done here. I think, for example, this Koopman von Neumann formalism, they do something like that. They embed the classical system into they create a Hamiltonian, as in with position and momentum variables. I'm not sure exactly how. I guess to some extent it depends on what one means by Schrödinger equation, but I'm not sure how that would be done for a general ergodic measure preserving dynamical system. So, for example, the class of techniques that I described here, perhaps not with all the bells and whistles, not all the like algebraic structure of the RKHS and so on. They can certainly be applied for something like a Lorentz 63 dynamical system, where you could have spaces of functions defined on the Lorentz attractor, which is a non-smooth set.
Excuse me, we are kind of next speaker is in 2 minutes.
Oh, okay. I was just going to wrap up. Yeah. So I'm not sure how these approaches would work in that context. I think the way of setting things up with sort of feature maps and so on would be potentially generalizable to situations where you have non-smooth attractors.
So the rotations may embed, but the more non-trivial ones, you need this extra machinery probably.
Yes, I think in the more trivial, the less trivial one, you would probably have to sort of relax some of the conditions that we have imposed here. And it's an interesting problem how to do it.
Thanks, Dimitris.
Thank you very much.
Right. Okay.